Well, hey there, guys. Mr. Carlson here. Let's talk about covalent bonds and molecular geometry. First of all, let's remind ourselves what a Lewis dot structure is. So, when we draw a Lewis dot structure, what we are doing is we are showing how many valence electrons that element has. So, remember, let's come back to the periodic table here. We learned that all the elements in group 1, the pattern there was that they have one valence electron. All the elements in group 2, they have two valence electrons. If we come over here, the elements in group 13 have three valence electrons, and then we can just follow that pattern from there all the way to the end. These transition metals in here, they've got some different rules because they got those d orbitals that kind of act as valence electrons as well. So right now we're just going to worry about these two columns here and these columns over here in the p block for looking at these valence electrons. So if I have to draw a Lewis dot structure for barium, for example, well, barium is right here. It's in group 2, which means it's got two valence electrons. So it would have one, whoops, hold on, got to get the white marker here. One, two dots around it to show it's got two valence electrons. As, which is arsenic, come over here. It is in group 15, means it's got five valence electrons. So 1, 2, 3, 4, 5 valence electrons. Bromine is in group 17, therefore it has 7. So 1, 2, 3, 4, 5, 6, 7 valence electrons. Now this is going to be important when we're writing out our Lewis dot structures for the molecules that we want to do. So right here, this is just a Lewis dot structure just for one element, but we're going to need to use this when we start making covalent bonds. Let's also remind ourselves the differences between an ionic bond and a covalent bond. So if we're dealing with ionic bonds, this is where we've got two things that have a really large difference in electronegativity. We just finished up a unit when we were talking about what electronegativity is. Remember, we said that electronegativity is the ability of an atom to take electrons or attract electrons towards it. And we said that these nonmetals over here, things like fluorine, oxygen, sulfur, chlorine, these guys are really electronegative, and the metals are not very electronegative. So what we see happening is that these nonmetals, because they're very good at stealing electrons, is that they will take the electrons, these valence electrons that these metals have, because they don't really have a good hold on their electrons. And so that's how those bonds form. And those are called ionic bonds. So that's going to be between a metal and a nonmetal. Some examples would be like sodium chloride, magnesium oxide, or calcium fluoride. I have a metal attached to a nonmetal. And because there's such a large difference in electronegativity, we can think of it as like a transfer of electrons. Whereas with a covalent bond, this is where the electronegativities are pretty similar. And for this, we see it's typically between two nonmetals that are bonding. So for example, if I have a Cl2 molecule where I've got two chlorine atoms that are bonded together, or H2O where I've got two hydrogens bonded to an oxygen or CO2. So if we think about this, for the ionic bonds, again, because there's such a large difference in those electronegativities, chlorine is so much stronger than sodium, it's going to steal that electron, or there's a transfer of that electron. And since sodium can be thought of as losing that electron, that means it's now going to be an overall positive charge. Chlorine, because it gains that electron, is going to have an overall negative charge. And that's what bonds those together. That's why they form an ionic bond, is because we can kind of think of this as like two magnets where I've got this positive side, this negative side. opposites attract, just like two magnets, and so they are stuck together. They are bonded together like two magnets. And we get these structures like this, these lattice structures, where we've got these alternating positive and negative charges. This would be the Na plus, and these negative ones here would be the Cl minus. And they just kind of form these really big crystal lattice structures of alternating positive, negative charges. But with the covalent bonds, it's a little different. With covalent bonds, instead of a transfer of electrons, now we get a sharing of electrons, because both of these, like in a Cl2 molecule, they both have the same electronegativity. So one of them is not going to take the electron. Instead, they're going to share these electrons here. So I've got this Cl atom by itself right here with its 7 valence electrons. I've got another Cl atom right here with its 7 valence electrons. And so when they come together, these two electrons here are going to be right here, and they are going to be shared between these two atoms. And so when that happens, now if I count up for this guy here, he has 2, 4, 6, 8 valence electrons, which, remember, that's what they want to have. That's called the octet rule. They want to have those 8 valence electrons because that's what's going to make them stable. And since these are being shared, I can also count these 2 electrons towards this atom as well. So he's got 2, 4, 6, 8. And so they now form that covalent bond because they are sharing these 2. And the way we would draw that is just like this. We put this dash right here. This dash represents those 2 bonding electrons that are shared between this guy and this guy. Now, when we've got a covalent bond, we would refer to this as a molecule. So if I've got a sharing of electrons to form a covalent bond, we refer to that as a molecule. But if we've got an ionic bond where I've got a transfer of electrons, that would actually be called a formula unit, because they don't really form these kind of molecules like this. They form these repeating patterns, these crystal lattice structures, or what we would refer to as these formula units. So that's the differences between the ionic bonds and the covalent bonds. In this, we're going to be talking more about how we draw Lewis structures for these covalent bonds, which again are going to be typically between 2 nonmetals. So our steps for drawing out these Lewis structures: as long as you follow these steps in this order, you should have no problems figuring out how to draw the structure for each one of these. The first thing you need to do is you need to add up how many total valence electrons that you're getting from each of the atoms in the compound. After that, you're going to put the singular atom in the center, or it's going to be the one that's the least electronegative, and we'll look at a couple examples here in a second. For the third part, you're just going to draw in the bonds first. So you're going to draw in those lines first to connect the atoms. And remember that each line represents 2 bonding electrons. And then the last part, you're just going to put whatever electrons are left over, you're going to put those on the most electronegative atoms first to complete the octet on each atom. So let's take a look at a few examples. Let's do this CF4 molecule. So first, let's do step 1. Let's add up how many total valence electrons that I'm getting from everything in this. So I've got 4 fluorine. So again, if we look, fluorine is right here. I've got 7. So 7 times 4, I'm getting 28 electrons from fluorine, and I'm getting 4 electrons from carbon. So that's going to be 32 electrons total. So now I've got my how many electrons that I want to show. That's how many I need to represent within that Lewis structure. Step 2, let's put the singular atom in the center, or in other words, the least electronegative one. Here's our singular atom right here, carbon. And we know that just by looking at the periodic table, by the way, it's further to the left than fluorine, so I know this is less electronegative than fluorine. But anyways, let's come back here. So I'm going to put carbon like this, and then I'm just going to draw bonds to connect the 4 fluorine atoms. So I'm going to go 1, 2, 3, 4. I'm going to put an F at the end of each one, and that gets me through step 3, right? I've drawn the bonds in, and so right now in this Lewis structure, I've got 2, 4, 6, 8 electrons drawn in there. I need to represent 32. Now, for step 4 here, the remaining electrons that I have are going to go on the most electronegative atoms first to complete the octet. So, in other words, we want to make sure that each atom right now within this structure should have 8 electrons around it in the end. They all need to have a complete octet. So right now carbon has, because remember, these electrons here are being shared between these two. So these 2 electrons are counting towards carbon. They're also counting towards fluorine. So carbon right now has 2, 4, 6, 8 electrons. So carbon right now has an octet. But each of these fluorines only has 2 electrons around it. And so what I'm going to do is put the remaining electrons that I've got, 2, 4, 6, 2, 4, 6, 4, 6, 2, 4, 6. So now I've shown that each fluorine has 2, 4, 6, 8 electrons around it. Let's count up the total amount of electrons that I've got. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I've got a total of 32 electrons, which is what I need to have, and each atom has an octet of electrons. I am done. This would be my Lewis structure for CF4. Now, here's the thing about this octet rule. There are a few exceptions to this, as there's exceptions to everything that we do in here. So sometimes not all atoms will satisfy that octet rule, and that's okay. So here's our exceptions to that rule. Boron and beryllium, they can be stable with less than an octet. So whenever we see boron, we won't see beryllium that much in these covalent bonds, but boron we will. But if we do see these two, they can be stable with less than an octet. So we're going to see these guys with like 6 valence electrons. So if they can get 6 valence electrons around them, they can be stable with that. And then the other thing that we can see is that elements that are in period 3 and above, period 3 and above, here's period 3, whoops, here's period 3. Anything that's above that, those elements have the ability to form what is called an expanded octet, And the reason for that is once we get above period 3, they have those d orbitals that they can work with to kind of hold more of those electrons. Whereas before that, things like carbon, nitrogen, oxygen, fluorine, they don't have those d orbitals where they can take on more electrons. So things like nitrogen, carbon, oxygen, and fluorine, those guys are never going to be able to hold on to more than an octet. But once we start getting to these bigger elements, like sulfur, chlorine, bromine, iodine, those guys can form what is called an expanded octet. So let's get a couple more examples of drawing these out. How about BeCl2? So let's do step 1. Let's add up how many electrons that we need to show for this. So I've got 2 chlorines, so that would be a total of 14 electrons, plus for beryllium, it's got 2 valence electrons, so 14, 15, 16 electrons is what we want to show. We're going to put beryllium in the center. We're going to have our 2 chlorines attached to it. And so now we want to add up to get 16 electrons. I'm going to put those lone pairs, is what we call these electrons here. Electrons that are, these pairs of electrons that are non-bonding. We call those lone pairs or non-bonding pairs. So I'm going to put these lone pairs here around each chlorine so that each one has an octet. So let's see, 2, 4, 6, 8, 10, 12, 14, 16. And so I am, wait a minute, 2, 4, 6, 8, 10, 12, 14, 16 electrons, and I am done with this Lewis structure because remember beryllium, we said, was one of those exceptions to that octet rule. And so I don't have to put any more, I don't have to make sure that there's 8 electrons around beryllium. He's good with less than an octet, and so I'm done with that Lewis structure. Let's try another one. NH3. I've got 3 hydrogens and 1 nitrogen. Nitrogen is right here in group 15, so 5 valence electrons, and then hydrogen has 1 valence electron that it can work with. And so for this, I want to show 5, 6, 7, 8 valence electrons is what I want to show for this. So we're going to put nitrogen in the middle. We're going to have 3 hydrogens. By the way, you could have drawn like this hydrogen up here on the top. That would not have mattered in this case. We haven't talked about what different shapes these are going to form yet. So at this point, you could have drawn that any way you wanted to. You could have drawn it like this if you wanted to. When we get a little further here, we'll see what kind of shapes these will form. But right now, it doesn't really matter. So right now I've got 2, 4, 6 electrons. I want to show 8. Now hydrogen is going to be another exception that we didn't mention here. Hydrogen, remember, hydrogen only has 1 energy level, and that first energy level can only hold 2 electrons. So hydrogen never wants to get 8 because it can't handle 8. The only thing it can handle is 2 electrons. And so right now, hydrogen, when it forms this bond, has a full outer shell with those 2 electrons. Hydrogen cannot get any lone pairs on it. It will never have lone pairs on it. And so in this case, when we see that hydrogen is like this in a bond, it is stable. It doesn't need any lone pairs or non-bonding pairs of electrons around it. But nitrogen here, we're going to put that other 2 electrons on nitrogen because he does need 8 electrons around it. So 2, 4, 6, 8 for nitrogen. And then each of these hydrogens is getting 2 electrons from these bonds. And I'm showing a total of 8. And so this one's done for NH3. ClO minus. For this one, we're going to have to take into account the fact that this is a polyatomic ion with a -1 charge. So oxygen has 6 valence electrons, and I've got chlorine as well, and I'm also going to have to add in this other electron here. So I want to show 14 total electrons in this case, 14 electrons, because of this extra negative charge. So we're going to put Cl bonded to oxygen. So right now I'm showing just 2 electrons, and we're going to put our lone pairs around each one. Let's add them up. 2, 4, 6, 8, 10, 12, 14, and I'm done with that one. How about NO2 plus? So now this time I've got this plus, which remember means that it's lost an electron. And so for this one, so I've got 2 oxygens. That's 12 valence electrons total from just the oxygens. 12 plus 5 from the nitrogen. So that's 17, but I want to subtract one of those because of this plus. So actually a total of 16 electrons is what I want to show. So I'm going to put NO2, and I'm going to put my lone pairs on here. each one. Nitrogen as well. And let's see, let's add this up. 2, 4, 6, 8, 10, 12, 14. Uh-oh, now we're running into a problem here. Because if I look, right now the way that I've got it drawn, I have 8 electrons around each. So each one has got the octet rule satisfied, but I've got more than 16 electrons here shown. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's not going to work, is it? So now I got to figure out something else to do here. And what's going to happen is, let's take away these electrons here. So right now I've got 16 electrons, don't I? 2, 4, 6, 8, 10, 12, 14, 16. So that's it. That's all the electrons that I have to work with. But nitrogen doesn't have 8 around it. So what I'm going to have to do here is I'm going to actually have to form a double bond. And how this is going to work is we're going to think about maybe these 2 electrons right here. Instead of being a lone pair, what they can do is they can form a double bond right here. So I'm going to redraw this right here. So a double bond where I've got 1, 2, 3, 4 electrons here between this nitrogen and this oxygen. And I'm going to put those other lone pairs like this. And so if we look, oxygen still has 8 around it, doesn't it? 2, 4, 6, 8 electrons around this oxygen. And I'm going to do the same thing on this side. These 2 electrons are going to go as another bond right here. So another double bond between nitrogen and oxygen. Same thing, put those lone pairs on there. And now I'm still showing 16 electrons, and each atom has 8 electrons around it. So if I count it for this oxygen, 2, 4, 6, 8. Nitrogen in the middle has 2, 4, 6, 8. And this oxygen, 2, 4, 6, 8. Total is 16. And so there's my Lewis structure for NO2. So sometimes you're going to have to kind of play around with the electrons that you've got, and you may have to form a double bond. Sometimes you might have to form even a triple bond in those. So you're going to have to do some trial and error for some of these molecules to get that total of electrons to fit with the molecule that you're working with. Let's try a couple more, some bigger molecules, like this H2SO4. This is sulfuric acid. For this one, you might be a little confused, like, well, let's see, I've got like 3 different things here. How do I know which one's going to be in the center? What's attached to what? So let's think about it like this. We know we've got this H2, so I've got 2 hydrogens, and then this SO4, which is a polyatomic ion. So I'm going to start by drawing out this SO4 first. So like this, SO4. Now, hydrogen is never going to be, it's always going to be something on the end of something, because it can only form one bond, and that's it. So for this, it doesn't matter where we put these 2 hydrogens, but I'm going to put it on one of the oxygens for each one, because I don't want to put it on this sulfur. So I'm going to put it like this, each hydrogen like this. And now I've got, again, I could have put those down here. It doesn't really matter at this point. And so now I'm showing, let's see, how many electrons do we want to show here? I've got oxygen, which has 6 times 4 is 24, plus another 6 from sulfur gives me 30, plus another 2 from hydrogen, so 32 electrons is what I want to show. Let's see, I've got 2, 4, 6, 8, 10, 12 electrons, so let's subtract that out. I need to show 20 more electrons. Well, let's put on these oxygens here so that each of these has an octet. And then same thing for these oxygens here. We're going to put 2, 4, 2, 4. And let's add these all up. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and all of these have an octet around it, and that would be my Lewis structure for H2SO4. How about this one? CH3OH. So same thing. What I'm going to do is I'm going to first make this CH3 part of this. CH3. And then I've got this OH. Now remember, hydrogen cannot be like in the middle, so I can't do like another H and then an O, because hydrogen can't have these two bonds. It can't have those 4 electrons around it. It can only have 2, so that's why I got to flip these around. And it's going to be O here, and then H there. All right, let's see. How many electrons do we've got? So we've got 6 from oxygen, 4 from carbon. So that's 10. And then 13, 14 electrons is what I want to show. So right now, 2, 4, 6, 8, 10. And then I'm going to put the rest of the electrons on oxygen, right? Because he needs 8. Right now he's only got 4, so I got to put 4 more on there. Carbon has 8 around it. Each hydrogen has 2, and we are done with that one. All right, last one. SF6. This is a molecule called sulfur hexafluoride. Let's see here. So for sulfur hexafluoride, I can already see I've got 6 of these fluorines that are going to be attached to one sulfur. And so when we do this, we can see that this is an example of our expanded octet. So F, 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 F. And already I can see that this sulfur has 2, 4, 6, 8, 10, 12 electrons around it. But remember, sulfur is in period 3 right here. And so anything that is in period 3 or above can handle that. It has enough room to take on those valence electrons. And for this, I'm going to put the rest of those non-bonding pairs here around each fluorine. This one's going to take a little while. There's a lot of these on here. And there, I would be done with that one. So hopefully that gives you an idea of how to at least draw these Lewis structures. And in the next video, we'll look at things like resonance and how we can draw kind of different versions of these Lewis structures.